Hey, now this is probably going to be the best lesson, or at least the third best lesson of this unit. Probability-wise, let's get into it. Just a quick recap from yesterday. We learned the addition rule last time, and the addition rule in its formal meaning is the probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. And basically what that means in its own intuitive addition rule is or means add. You just have to remember that if you're adding two events together and there's any overlap, like in a Venn diagram you see it visually, then we have to subtract that overlap because we don't want to count it twice. And that's kind of what we talked about with that addition rule. Now, there are other intuitive rules, and this is something you maybe know, like what's the chance of getting a heads and then a heads again if you're flipping a coin? Well, you can do 1/2 times 1/2. So anytime you see the word and, I guess, or then, another one would be then, that generally means multiply. So we're going to get into that a little bit more today. This is the lesson 5.3a, an introduction to the multiplication rule. So we're still looking at finding probabilities of events, but we are specifically going to get into multiplication rules. So, little vocab here. What are independent events? We've used that term before. So events A and B are independent if the occurrence of one does not alter or affect the probability of the other. So if the second event B, like if one does not affect the other, okay, if B does not alter the probability of A. Whereas if they do, like if the result of the first event affects the outcome of the second event, then it's called dependent. So we need to know the difference between independent and dependent events. So let's look at a couple examples here. I'll just look at one at a time. Here we go. Side by side, we have very similar examples. Let's look at the one on the left. A box contains 4 red marbles, 3 green marbles, and 2 blue marbles. One marble is removed from the box and then replaced. Another marble is then drawn from the box. What is the probability that the first marble is blue and the second marble is green? Okay? So, if we want both things to happen, it's an and that's when we said we're going to multiply. Right? So, if we say the probability of blue and then, maybe I can even use the word then, green, the probability of getting blue was 2/9. There's 2 blue. Multiplied by the probability of getting green, which is 3/9 or 1/3. We can multiply and reduce, or we can reduce diagonally. Ultimately, you get 2 27ths. So what I would be doing here is changing this to be 1/3. So I get 2 27ths. That is my probability. A blue, then a green. Example 2, side to the right side, looks very similar. But it says a box containing 4 red marbles, 3 green, and 4 blue. Or sorry, 2 blue. One marble is removed from the box and then is not replaced. Another marble is drawn from the box. What is the probability that the first marble is blue and the second marble is green? So the same thing, we still have an and, however, it is not replaced. This is an example of something that would be dependent. The second one is affected by the first one. But the first one still has to happen for this to work out. So a box contains 4, so we're going to do the probability of a blue again, and then a green, would be 2/9 times, now what's the probability of getting the green? We took that one out. There's only 8 left. it is still 3. 3 greens, but it's only out of 8 now. So that is what changes, and it changes the whole probability. So now I would get, ultimately I'm going to reduce here to 1 and 4, which gives me 3. Oh, actually I can reduce more. Let's do that. 3/9 I can reduce here. That's going to be 1/3. I get 1/12. It's a slightly better probability than if I didn't, or if I did replace. But this is the difference. And it happens to deal with the independent versus dependent. The first one are independent events because it doesn't matter what happens with the first one. The second one is it's not changing anything. You're putting it back, so you still have the same chances. The second one, it's affected when you don't replace that marble. All right. Now, notation for this. This is a new notation. It's worth writing down. This is a conditional probability. So this is the probability of A given B is how you would say that. It's saying, what's the probability of A happening if B already happened? This is a conditional probability. And a conditional probability is the probability of event A given that event B already happened. So we're not saying 2 events are happening. We're just saying what is the probability of event A still, given that B already happened. Sometimes it won't change it. Sometimes it will. Okay? But it's a conditional probability. And there just so happens to be a formula on your formula sheet for this, which we're not going to really use a lot today, but the probability of A given B is going to be equal to the probability of A and B divided by the probability of B. All right? So this is just on your formula sheet. We'll get into that more later. Now, we need to discuss this multiplication rule because it is different, slightly different for independent versus dependent events, as was shown in that last example. So for independent events, if they're independent events, it's just, we're talking about the probability of A and B. So 2 things happening simultaneously. It's just the probability of A times the probability of B. But when it changes is when we have dependent events. Okay? So for dependent events, the probability of A and B happening is equal to the probability of A times the probability of B given that A already happened. Or we could rewrite it as the probability of B times the probability of A given that B already happened. So either way is fine, but that's how it changes. The second probability can change depending on if the first probability happened or not. So let's look at some of these situations. I've got a whole bunch of them, and we want to also identify, is it independent or dependent? So number 1, rolling a 6 and then a 5 with a die. Does the second thing, is that affected by if you roll a 6 first? No, these are independent. Independent events because you can't, like, it doesn't change the die if you roll a 6. It still is a 6-sided die. So I'd have a 1/6 chance times a 1/6 chance, which is 1 out of 36. All right, That's the probability of a 6 and then a 5. Number 2, tossing a coin 3 times and getting 3 tails. So is the second one affected by what you get the first time? No. Those are independent events. So it's still just a 1/2 times a 1/2 times a 1/2, which is going to get you a 1/8 chance of that happening. Not super high. Let's keep going. Rolling a 6 Yahtzee on the first toss of the dice, meaning you're getting a 6, a 6, a 6, a 6, a 6. That's 5 sixes. In case you didn't know what that meant. Okay. Is rolling each 6 dependent on one before? No. They're 5 different dies. So you have a 1 in 6 chance each time for each die. So you can just multiply them all together. Which doesn't very good chance of happening, but it can happen. How about drawing cards? Drawing 3 kings from a standard deck of cards without replacement. Here's where these are dependent. Without replacement, that's definitely affecting the next draw. So if I draw a king, I have a 4 in 52 chance. But then I have 1 less king, and I have 1 less card overall. So my second chance is a 3 out of 51. Then if I really drew it again, I have only 2 kings left, and I have 50 cards left. So my chances are changing each time, and you can find that probability. It's because we said without replacement. Likewise, at number 5, drawing a red, then a white, then a blue marble without replacement. Again, without replacement. So it's affecting, you're not putting it back in there, so the probabilities are changing each time. So if there's 5 reds, 3 blues, and 7 whites, if you're going to draw a red, you have a 5 in, 15 chance. But then if you actually draw that, this is very specific, we want to then draw a blue. So now we're down to 14 marbles. There's still, how many blues? 3 blues. But then we're down to 13 marbles. Say you actually did that, and we want to draw a red, then white, then blue. So the blue would have been here. The white would have been the 7. So I'll change that. And again, you can calculate those probabilities either in fraction or probably decimal form because of the numbers. But I guess either way would work. I'm not going to do that just for the sake of the actual numbers we have. Actually, this one's not too bad, because you can reduce a lot. It ends up being 3 out of, not too crazy. I just want to get the idea here, though. Let's keep going. Number 6 and number 7. Of a family of 4 children having all daughters. Or, like my family, I have all sons. Is that, what is the probability of that happening? Does one affect the other? No. Each time you have a 50% chance. So it is 1/2 times 1/2 times 1/2 times 1/2, which gets you 1 out of 16. Which is like, I don't even know, 6-something% chance. How about of guessing correctly on all 7 questions on a true-false test? Does it affect if you have one correct or not? No. These are independent as well. But I want to do this one because it's written slightly different. If you have 1/2 chance every time, you can multiply that 7 times, but you can also just write that as to the 7th power. So you don't have to write so much. I'm guessing, what's the probability of guessing all 7 questions on a multiple choice test? Well, we have 4 choices. You have a 1 in 4 chance. We're doing it 7 times. We're going to do that to the 7th power. That's how you can find that probability. These are independent as well. Doesn't matter one question to the other. We've got 2 left. Drawing 4 aces from a standard deck of cards with replacement. So putting it back. So you have a 4 in 52 chance, and you put it back. If you get it, you want to do that 4 times in a row, you're going to just do that to the 4th power. Or multiply 4 50 seconds times itself multiple times. Again, that's independent. We are replacing them. Lastly, of randomly selecting 2 teachers who hate dry erase boards when it's known that 2% of all teachers hate dry erase boards. Well, we have a 2% chance, and we want that to happen 2 times in a row. Now, it doesn't say with replacement or without replacement, so that might affect it. So this is worth thinking about. Might be dependent. If you can have the same person twice, then it's fine. Then you can just do it to the second power. Might be dependent, which would affect which would then affect that. So looking at whether one affects the other or not is big when it comes to how you'd use that multiplication rule. All right. Just a couple things yet to think about. If the probability of an event is less than 5%, 0.05, then it is considered mathematically unusual. We've talked about that before. So what we're saying is the probability of whatever event is less than 0.05. Then it is unusual, it is rare, it is statistically significant. In a normal curve, we talked about how 95% of the observations are within 2 standard deviations of that, so that's why 5% is rare. But if we go back to any of these, we can determine what's rare and what's not. Like these first, like actually rolling a 6 and then a 5 on a die is pretty rare. You'd have to take your calculator and figure out the exact decimal versions of them, but it's considered rare. 1/8, though, however, is not rare. 1/8 is not less than 5%. So again, 1 divided by 36 is like 0.027. I want to go back to that 1. So I have 4 boys. Is it rare to have 4 boys? 1 in 16 chance. You know what 1 over 16 is? It's 0.0625. So it might seem rare, but based on our 5% rule, it's not quite considered rare. You'd have to have 1 more in a row. So that's the idea of things that are rare. All right, last example, I'm going to deal with a little bit of dice. If you're rolling 2 dice, what are all the possible outcomes? Well, you could get a 1 and then a 1, a 1 and then a 2, 1 and then a 3. You get a whole bunch of different options. I have them listed here. These are all the possible ones. White is the first roll, blue is the second roll. There's 36. You're 6 by 6. So you have to picture this when we're dealing with different probabilities. Like, what is the probability that your sum is 8? Okay? Seems like a random question to ask, but it's fair game. You've got all your possibilities. How many of them have a sum of 8? Well, we should hopefully know 4 and 4. But you could get a 3 and a 5. You get a 6 and a 2. I believe those are all the ones that are summed to 8. So out of the 36, you've got 5 options. How about a sum of 11 and then a sum of 6? So we're rolling 2 of them now. So sum of 11 would be you got to find all the ones that sum to 11. It's just 5 and 6 or 6 and 5. So there's only 2 of them. So our chances are already kind of low. But let's just say sum of 11, we have 6 and 5, 5, oops. Um, 6 and 5. There's a mistake here. That's why this is supposed to be 5 dots here. There's a mistake. Whew. So there it is. So that's 2 out of the 36 possible. And then a sum of 6. So the sum of 6 would be, what do we got here? A 3 and a 3, a 2 and a 4, a 1 and a 5, and then all of these. So that's 5, the sum of 6. 5 out of 36. And we can find those probabilities. A little bit of reducing helps us out. This becomes 1 over 18, but end up getting 5 out of some big number. So 36 times 18. So it's not real common, not real likely. It's actually considered unusual. Which, by the way, that number is 648. So, I want to leave you off with 5 intuitive rules that we're going to be expecting to know. That'll help you get a 5, especially when it comes to probability. Probabilities are between 0 and 1. Okay, inclusive, 0 and 1 can be counted. Complement rule, we talked about that, how the complement of something is everything other than your one event. So, two things that are complementary add up to 1. Or means add, but beware of the double counts. That's where we can subtract for events that aren't mutually exclusive. Subtract the middle. The word given usually means divide by the given, and that's where we're going to get into that next time. Going to get into more of those given, those conditional probabilities. And the word and means multiply. We just got to adjust if they're dependent events. But that's day 1 on the multiplication rule. Like I said, next time we're going to get into day 2. It's going to be more with those given or those conditional probabilities. So this is section 5.3a. We'll see you next time.